So, hello, welcome, bienvenidos, herzlich willkommen, every language, but I keep this in English. This is a presentation from Thomas Weibler, the CTO, and myself, and yeah, it's also analysis about a little bit of power consumption, but we are looking more into the transceiver side, and we want to see what happens with these devices on high temperatures, what the bit error rate is, and what are the influences. Temperature is one parameter, fiber length is another parameter, and we have a small overview here. Can you see the cursor? Is it? Ah, yeah, here it is. Ah, great. So intro is halfway done. I started with intro a bit. There's just one more picture. Like every good story, there will be a sequel. So topic 3 and topic 7 are missing. This will be in another talk, most likely end of this year or next year, depending on what NOC you're going. So yeah, this is like a continuation of a series of stories. And we are going to talk a little bit more about the bit error rate and what you can do nowadays on the transceivers. Of course, distance is involved. Temperature is a very important topic. A problem. We suffer a lot in the data centers when cooling systems are failing. What happens with the transceivers? Do we have to unplug them, or can we keep them running up to which temperature? This is what we are going to find out. And I also will present you a live demo. Hope you will enjoy it with our new product here, the Flexbox. And yeah, of course, like every good presentation, we have takeaways. And getting to the last slide of our introduction, modern transceivers usually have a DSP. This is a QSFP one, and these DSP, these chips have a special feature where you have forward error correction, which you can apply. Sometimes you have to do this with your network gear, but these transceivers can do it by their own. But there are way more features like bit error rate tester or optical signal-to-noise ratio measurement. And we are going to look into these features a little bit deeper in this presentation. But before we really dig into this topic, I want to talk about 2 points of views. The first point of view is signal-to-noise ratio. What happens, for example, when I'm talking in a very high, loud volume, you can perfectly hear me, but if the audience is a little bit louder and talking each other, it becomes difficult. So no matter how loud I talk, if the noise level is higher, it's difficult to decode what I'm saying. So basically, this is the idea of signal-to-noise ratio. You always have some noise, some ground noise in your optical signal, in your electrical signal, which, by the way, when you look up literature, you see electrical ESNR. Usually we don't put the E, so SNR is really the electrical side. Usually when you see OSNR, it's really the media side, the optical side. And yeah, the difference between that, logarithmic difference, is the SNR. More interesting for us, which is the point of view, I'd say, more of a network operator or data scientist maybe, we don't care so much about the signal. For what we care more is how reliable are sent our strings of bits or bytes. And it's a pretty simple formula, obviously. Number of erroneous bits divided by total number of bits is your bit error rate. And measuring that is what really matters more. But of course, the optical signal-to-noise ratio has an influence on that. So how was our experiment built up? So basically, we removed the head of the Flexbox, since we also need to cool down this device if we want to keep running transceivers of, for example, this one is an 800G transceiver for a longer time with some breakout cable, and we put a heatsink on it and just blow some cool air into it so we can keep it at a very stable temperature. So what I'm going to show you here are some diagrams, but I want to keep this a little bit interesting, so I picked out the most interesting transceiver. Particularly, we will start with the ER 40 kilometer one, because there are some setups you have to look for, but we have more tests, so if you're interested, just reach us, and I can show you more about what we have discovered in these devices. So how was our build-up? Basically, you get a couple of fibers, so through fiber drums, you tie them together, and up to 60 kilometers, we tested the bit error rate. What you need is obviously the transceiver, but you have to watch out also how you connect it, because my goal was to test it with 2 meters with a very short cable, but also with a very long cable, 60 kilometers, and you cannot just plug it in. You have to watch out for attenuation. Usually when you check our job, you can look at specifications like those, how the laser will be turned on with which maximum power it will transfer, and here we have around 8 dBm, and the reception side, what is the maximum it can receive, which is -3, so the difference of those is 11, so we have to attenuate 11, because if you don't do that, you might damage your transceiver. So watch out for the ER transceivers, because this is something that can happen, but it also makes it a little bit more difficult to analyze our studies, because I had to attenuate at certain distances. So with 2 meters, I have to attenuate with a strong attenuation of 11 dB, and I kept the first 3 at the same pace and just looked into the diagrams what bit error rate we get. This is still prefect, and this red rectangle you see here is an area out of the specification. So 2.4 times 10 to -4 is a specification by the IEEE 802.3 dB, where it says it is considered Ethernet if you are working in this range, but beyond that it is way too erroneous. Now I consider this limit very generous. You will see why in the next slide, but actually what is interesting here is, I mean the attenuation obviously with 30 kilometers, 40 and 50 affects the bit error rate, but more interesting is how the temperature has not that big of an influence. And now you can see these red circles here, which are jumps. It like jumps down. So here is a message to you. If the temperature increases, the quality increases. This doesn't make sense, right? Well, it's not what really happens. So first of all, the jump is not that much. It's going down with a bit error rate, yes, but it starts to get worse again. The thing is, when the transceiver gets warmer, usually what the transceiver tries to do in its control circuit is to keep a stable temperature on the laser. In order to do this, the laser has to be cooled down as well. Usually you have some elements this does really take out the heat, and with that you need more power. So it's investing more power, it's targeting a certain power, and that's the reason why you have this effect that it jumps down a little bit, but it really does not improve. So high temperatures are not a good idea, obviously, but you can see there is an approach trying to keep this stable. And with another transceiver I'm going to show you, it will be more interesting. Now, getting back again to the bit error rates, this is another formula where you can read specifications about the gating time. What is the gating time? Well, actually, you just take your formula, your delta T is the gating time in this case. You put it here, and quite simple. But it's also important to understand this equation, because, you have your number of samples, but there's this Gaussian noise effect. If you measure an error on your transceiver, it might be a wrong measurement. In order to really get to this benefit of doubt, what is usually done is you take a sample of 100 errors, you send them through, you assume a bit error rate you want to have as a target, and from that you can calculate your gating time. And in this example with 10 power minus 12, you have a gating time of 16 minutes, right? Which means in 16 minutes you can expect an error between 1 and 100 if you have a rate of 100 gigabits per second. So this is how you deal with this gating time if you see it in your specifications. Now I use the same formula for the specification of IEEE, and here you can see up to 100 errors after 4 microseconds. So if you ask me, that's quite a difference. So message here, keep your bit error rate as low as possible, obviously, right? Now let's look at the coherent transceiver. The coherent transceiver is quite interesting, especially set R1, because it has an advantage I like a lot. But before I get back to the next diagram, which is may easier to interpret, you will see, compared, which is a relief if you ask me. The other one was already complex enough. This cooler was taken from an old Cisco 800 router, and it has good performance. So you just blow cool air, and that's it. Where do we get these devices? Well, our CTO Thomas Weible, as Flexoptix, we have a friend who does a lot of recycling. So if you are interested in some topics like this, he is very good at recovering raw material. He takes this task of recycling old devices pretty seriously. If you're interested in some project like that, feel free to approach us, and we're happy to forward this contact. And anyway, this is a diagram with coherent, and we already have one advantage, that we don't need to attenuate, because you can take the coherent transceiver, plug in a 2-meter jumper cable, and extend it up to 60 kilometers with the different fiber drums, and it will not burn your receiver. And that is a nice advantage. So it really has more ways to moderate the X power with a given TX power. And as you can see here, the curves are more like constant, and that is really the goal we are trying to achieve. So even though you have high temperatures, really the goal is to keep the bit error rate constant. The only factor that cannot be influenced by the manufacturer, obviously, is how long your fiber will be. If you connect a longer fiber or shorter fiber. I mean, before you connect your fiber, normally you decide first what transceiver you want to take, which is convenient. But with a coherent, you're a little bit more flexible. The reason for that is it has more parameters. So it has a better chance in its control circuit to really moderate the values. And with that, it really achieves some sort of constantness, as you can see. It's not perfect, but it's almost there. And without cooling, it changes also a little bit. The bit error rate is very dependent as a rolling average on how much data has been flowing, since it's this simple formula which just counts the erroneous bits and the number of total bits. So you are tracking the past the whole time. And without cooling, this was running for a couple of minutes because it gets hot quite quick. So you really have to cool down these. Now let's get to more extremes and take a transceiver which we heat up to 120 degrees. Recently in one of our link posts we had some discussion about it. A guy who had a transceiver running on 100 degrees because the ventilation system failed, and he wanted to find out, was surprised that the transceiver still was working. So it was almost at the same time, so this topic comes and goes at times, but we wanted to find out how our transceivers behaves in extreme conditions. So what I have here is, here's a transceiver. I just put a trace in Microsoft Paint so you can see it because it's a lot of gray. We have some aluminum foil here, a heat gun that goes up to 600 degrees. And we, instead of cooling down this transceiver, we intentionally put heat on it in order to see how it would react. It was quite interesting because the first warm-up, I put a limit. In our software, we have an integrated limit of 65 degrees. We find this quite high. When it doesn't go down, we usually shut down the software. So I just wanted to see what curve we have here. And then I removed the limit up to 100 degrees. So I was looking around what would happen. And around 80 degrees, it started to stop. It reported with a loss of signal. The transceiver, after that, also stopped to be reachable from the Flexbox. But when I shut it down, turned it on again, and tested with 120 degrees, was this slide here, you can see the 120 degree point. It still worked. It went into a loss of signal, heating it up again. And I really put my limit on 120. I didn't want to damage this transceiver. I was a little bit afraid of it. So I repeated this experiment, but more of that in a later slide. What I want to show you here is in the cool down phase, we reached the original bit error rate. This is this purple curve you see here. So we hit this point at 70 something degrees. It goes hot when I started, but it goes down again. It stabilizes. So this transceiver, after having it operated at 120 degrees, still works fine. So I think that's a good achievement, but don't try it intentionally. It's just for your information what could happen if you go beyond high warning, high alarms. These are values you can read out from your network gears. Now, then we have the question about bit error rate and does it recover. So if you remove a cooler and put it back, should I get the original value? As I mentioned before, it's a rolling average value because you are counting the whole time the errors and the total number of bits. So actually, when you have a fact like the temperature goes up, obviously, yeah, that is what to be expected. It goes down, back again. But the bit error rate does not recover at the same pace. The reason for that is because it's dragging the past. So you might as well reset the transceiver if you have the opportunity. There are registers where you can write values and reset this counter. You should do it because if you just keep looking at the bit error rate in your network gear, you might be disappointed that now you see a worse value, but it doesn't mean that the transceiver all of a sudden is running at a worse quality. That is not the case. That's the reason why you might see this value. And with that, we get to the exciting part, our live demo. Let me just plug in this. And I want to talk about a topic I have hidden a little bit. Perf control plots. Here we go. Let's start this small script. Yep. Now it's waiting for the transceiver. Do we hear the clicking noise? Yep, here we go. The transceiver needs to boot up a little bit, but let me explain this graph, what you are going to see in a couple of seconds. So this is a bit error rate I have been discussing the whole time, so we are going to measure it right now. You will see the temperature with the QSFP28 transceiver we have plugged in. IX power is always interesting just to see how the signal reacts. And the OSNR also is here. OSNR has influence of bit error rate. As I explained previously, we are not so interested in that, but it's good to observe it. There are some extreme values, usually between 20 and 30 if OSNR is too low. Obviously, I cannot hear you, you know. It's difficult to decode, but beyond 30, the signal is too good, also doesn't work because you have quantum effects. So what the manufacturers usually do is specify to have an OSNR between 20 and 30, and as you can see, it's running fine at 23. Now there's a challenge because the memory between the bit error rate and SNR is shared. So what I'm doing here is the whole time writing into a register, it's called the diagnostic selector, and swapping the pages, and this makes it a little bit slower. What I can do here in my little software is turn off this page, and I'm not writing the diagnostic selector, so you can see it's a little bit faster now and smoother with the values, but we still have a good bit error rate here, so 2.5, 2.4, 10, minus 12. The temperature is increasing a bit, but yeah, it's more or less relaxed. Now let's have a look again at SNR. And in order to see that I'm not faking this, it's a real video, I'm going to bend this cable so you can see how it reacts. Let's bend it a little bit. So guess what Rx power are we going to get if I bend it too much, if I get into the loss of signal situation? Any idea what value it is usually? How far it gets down? Minus how many? Okay, I tell you. I bend it way harder, and the limit is at minus 40. And it's quite interesting how the OSNR also goes into 30. It would look like a good value, but as I mentioned previously, it's a flag that the hardware manufacturer is setting. It doesn't mean it is good, it means there's no signal. So yeah, a little bit weird sometimes, but it is what it is. So let's unbend the cable, and as you can see, you have a pretty healthy, normal IX power, and you can see over the time axis how much and how many times and how strong I bent the cable. Right, yeah. Let's get back. I can close this. Let's get to another experiment, this time with 250 degrees. This was quite extreme. So same heat gun, but this time a little bit longer, up to 250 degrees. I took a different transceiver, one that is more resistant to heat. So as you can see here, we have still the high warning, high alarm. You can read out through DDM, and what you should see in your network gear. For this transceiver, specified to 85 and 90 degrees. But I introduced a new value. I called it weird. Maybe some of you developers know why or what this 128 means, because if you have an 8-bit memory where you store your values, the first bit is a sign. So if you go beyond 128 degrees, you start seeing negative temperatures, which doesn't make sense. So I decided to correct this and just remove the sign, and you can continue to see what happens here. And around 125, it stops sending any signals, the signal is gone, and that was it. But I went beyond up to 250 degrees and then checked if the transceiver still works. As you can see, the label is not visible anymore, so it melted down. The Flexbox is still working. This is impressive. I wouldn't have thought that. But this transceiver doesn't work anymore. It boots up, you can read values out of it, but the X value is like 100,000-fold worse of what is detected. So for that, it's pretty much unusable. And that's basically it. Some takeaways. Bit error rate on direct detection transceiver depends on temperature and also fiber length, obviously. Bit error rate is rolling average, since we are counting the whole time. So you are dragging the path when you read bit error rate. Watch on this. There isn't much margin above high temperature and loss of signal, as you can see. So you have a little bit of tolerance. You can be lucky if you had 100 degrees, it recovers itself. But beyond that, most likely it will stop working. Now looking at the coherent transceivers, they benefit more of the properties of light, like for example polarization is a feature that it can detect, and with the polarization effect it has more ways to correct and recover the signal. And but the drawback is that, of course, it requires a DSP, a powerful DSP. It draws more power. As we saw in the previous presentation, these are more power hungry. And coherent do not depend so much on temperature, but it is because we have more parameters, a better control circuit with that. And whatever specified, you couldn't look for the Ethernet EEE, but it's really a generous value. But look at the bit error rate. That is for what you matter most, because OS&R between 20 and 30, you're fine. Doesn't matter into which exact value it goes. If the bit error rate is low, you're fine. And a little bit of AI pictures, because every presentation needs AI. So we just put this sentence and Flux AI generated these weird images. It's quite interesting what they can do, but anyway. Thank you very much. Any questions?
Yeah, are there questions in the room?
We have one. Or not?
No, questions online? I also, well, while we're checking online, I have a question. Yes. Just in the final slide, you mentioned about the bit error rate was not an instantaneous value, but a rolling average for the grey optics. What is that rolling average period normally? Do you know it's an average of the last 10 seconds, the last 10 minutes?
I would keep it running for a minute.
Yeah.
I mean, it really depends on many factors. You want to keep it running forever, obviously, but I think if you wait, if you have 800G, 10G with a gating time, you can calculate how many bits were pushed. So I would say the bandwidth really helps on that, but 16 minutes, as you saw in gating time, I think is a good value.
Okay.
So look at this, take a coffee, come back, and this is. I had another diagram. I didn't bring it. It's between 16 and 4 minutes. With another transceiver I tested, it was 4 minutes, and after that it really stabilized, and I let it running for 1 hour. Okay. So,
Yeah, cool. Thank
10 minutes, 16 minutes, 20 minutes, and you're sure.
So you've done a bunch of stuff with transceivers getting hot. It's very interesting. Thank you very much. A thing that I've noticed is that you get transceivers and industrial transceivers. That actually the big difference is like, the regular ones go up to 70-ish and the industrial ones go up to 80-ish, 85-ish. But on industrial ones, they go down to 40, as in minus 40. On the rating plates on industrial transceivers, they go down to like minus 40 degrees. And so my question is, have you done any experimentation with how cold you can take transceivers?
We have not, unfortunately. That is true, and we really need to see in our lab how we can build something like that. I mean, liquid nitrogen maybe,
liquid nitrogen,
but yeah, nitrogen, you have to use, I mean, we can cool down the transceiver, but these are extreme temperatures, and yeah, the electrical appliances we have also have to survive it.
The more interesting question that I wanted to ask, though, is on the industrial ones that go much colder, what's different about an industrial transceiver that means that it can cope with being cold? Like, what's actually the difference between a regular and an industrial that means that it can cope with being cold?
I still want to look into one. For what I have read, they are better.
I mean, are they just
They have
potted?
a different housing that protects the heat better, that distributes the heat
I've never
better.
taken one apart, but I mean, could they be like potted against condensation or something, maybe? I don't know.
I have to check.
That'd be cool.
But thanks for the question, I will note it.
The PC will happily accept your talk for NetUK2.
Yeah. Now, and since we have industrial ones, we will take a look. Thanks. Thank you.
Thank you very much, Gerhard.